give another 30 seconds in case someone come in last minute. Okay, so before the lecture, a couple of quick announcements. So PSET 2 is due today. If you haven't tried the PSET, definitely try it as early as possible, because this one requires a lot more effort than the last one. And reach out to Stefan if you have any issue with the auto graders again. So the PSET 3 will be out hopefully this Friday. There could potentially be some opportunity that there's a small delay to PSET 3, so it might be postponed to next Monday. So PSET 3 will be more on the geometric deep learning part. So the technical challenge in PSET 3 will more on the mathematical side as opposed to coding side. So it kind of more like a problem set with some math problems. Even though you might be solving it with a little bit Python code to code up. I think a couple of students asked about some like standard or requirement for the project proposal and final report. So I uploaded some instructions to the module called course project. The project proposal is due next Thursday, I believe, Thursday or Friday. So it will be submitted through the Canvas assignment. We'll be creating an assignment on Canvas with a due date of November 1st. So the project proposal will be more like a common kind of short proposal with about 1 page, but if you need more space, you could potentially use 2 page. But I think 1 page excluding bibliography or references. And I recommend font size no larger than 13 point. I think usually the overleaf use like 11 point. And then the outline, you can feel free to modify it based on what you think would describe the project smoothly, but these are kind of the potential like sections that you can include. Definitely remember to include the group member name and email, and the planned timeline will be important. And I recommend state clearly how you're going to evaluate your method and what metrics you're going to be looking at. As like even though you can change it in the final report based on what you find out, but it's good to think about it ahead of time. And then for the final report, it will be more like a research paper. Some people ask me again, like, what kind of, is it okay? Is it more like implementing something that already exists, just reproduce? So quick answer, as I mentioned previously, it should have at least some novelty, either on the methodology side or on the application side. It should not be a total reproduce of some work that already exists with like really, really minor differences. But you're not expected to make something that is guaranteed to work. So you can feel free to try out new things, even though it failed at the end, as long as you provide your thinking process throughout the project. It will still be highly valued. In terms of the report, it is due 1 week after the final presentation, so you still have some time to like collect feedbacks from your peers, and the final report will be submitted through the open review. It will be the same venue as where we submit the reading assignment. We will also give like meta review through the open review, and the final score will be basing on the final report and your presentation. Sorry, I forgot to mention the point. The project proposal takes 5 points out of the total. I think the total points for final project, and I think the final report and the final presentation are equally weighted. And in the final report, it's recommended to use a new RIPS template if possible, but you can also use whatever template you want. It's 10-page max, 8-page mean, excluding references. Font size should be no bigger than 13 point. And the outline will be pretty much similar like all the research papers in the computer science and machine learning domain. Usually involves abstract, there should be an abstract, but it will be in the template, and introduction, related work, methods, experiment, and discussion. And particularly at the end, please include a paragraph describing how you divided the work among the team members and basically who is in charge of what. So to help us better evaluate the each individual's effort in this project. So I think that's all. If you have further questions, you can ask them now or reach out in email. Let me know if you need any more information about these two. Okay, so let's start. Cool. So last time we talked about a very simple, we talked about kind of the challenges in learning from graph structures and relational data, and kind of prototype on the graph learning. And we mentioned about different types of machine learning tasks that can be done over a graph, including node level predictions, edge level prediction, and graph level predictions. Note that these are sort of like the training loss that you can apply to train the neural network, but they're not necessarily trained to be just a prediction task. For example, you can frame the prediction task as a generative task to generate graph and turn it into a diffusion or variation autoencoder model. And these all also involves kind of these three levels of prediction, because effectively we're kind of building a graph. The main idea behind graph neural networks or graph learning is to come up with a good equivariant machine neural network architectures that is able to encode the node, encode the graph into several embeddings. Particularly, we care about node embeddings, and sometimes also the edge embeddings and graph level embeddings. And the particular challenge in graph is to capture the invariance and equivariance for with respect to the permutation operation. Basically, the ordering of the node in the input data doesn't matter, or you should manipulate your output correspondingly with how you manipulate your input graph. So the key idea of graph learning architectures are basically through this kind of defining a computational graph based on local neighborhood structure of a node. Usually this is done through computing some message from the neighbors and try to aggregate the neighbors' information. Sometimes we call it message passing, such that the information can flow through this local computation graph defined by the topology in their neighborhood space. And particularly we talk about this simple case of one layer of graph convolutional neural net with skip connections. I will explain why a skip connection is used and where it is used here, but you can see that it's basically taking some average or convolution over the neighborhood embeddings, multiplied by some weight, and adding the embedding of the node itself. This is kind of what the skip connection means, and you could apply further deep learning, activation layers or nonlinear layers on top of these aggregated messages. So a lot of the architectures that we're going to describe today are also based on the same idea of defining some type of local neighborhood for message passing, and try to keep these invariance and equivariance to permutation. So if we look at the graph neural network, outside of just the GCN, it can be framed as a more general framework for graph learning, where the usually can consider graph neural network consists of multiple layers of GNN layers, where we need to consider how we design each of the layers, basically how we design this local message computation and message aggregation, and how we stack the layers together to propagate information further than one hop neighbors. And in the input side, we need to also think about how we come up with the training data, how we process the training data, and we also need to define different learning objectives that will define the training loss. Particularly, a single graph neural network layer comprises a two-step process. The computation graph of the single GNN layer usually comprises of two-step process. The first step called message or message computation. The second step called message aggregation. And so together of them, this is kind of defined as like a message passing framework. And you can see that usually the input to the layer is a set of node, and each node will be associated with some embeddings that's learned with the previous layers, and some neighborhood, which is usually noted as N of V, which is a set of node that is one hop neighbor of the current node. Usually you can define that with adjacency matrix. There would be some features related to each of the node in the input, and through multiple layers of transformation, these features will again become some type of embedding. And we'll go through the GNN layer, and then each of the node embedding will be updated through these two steps. After the aggregation step, you can imagine each of the node in the graph have an updated embedding. So in the message computation step, we can basically think of defining a function. MSG is kind of notation of a general way of computing the information. So it can be it can be developed into different versions. Basically, you can come up with different architectures to encode the information from the previous layer, and think of different way of transforming that information. This is all belong to the concept of message computation. For example, very simple way of computing messages, just do a linear transformation. This is what we see in the previous GCN prototype. And the aggregation step, again, it's a function that has to preserve permutation invariance. So it needs to be a function defined over a set, where you can see the notation here. The input is with the structure of a set, where each element in this set has no difference in terms of ordering. So we don't have any ordering of these input sets. A very common aggregator that preserves the permutation invariance are like summations, right, or average, or max or mean operators, and that these will be the most commonly seen operators over the input nodes. And the summation can be done with a weighted version. If your weight is not relevant to position or ordering of the node, that will still be permutation invariant. So one kind of common issue in graph learning is self-message. Sometimes if you don't consider the node itself and only aggregate information from the neighbor, your only the information of the node itself will get lost. So basically we don't want to just aggregate information from the neighbors, but also keep the information from the node itself in the previous layer. So this can be solved by just, when you do the message aggregation, also like add in your own message to the end of all the message from neighbors. So this can be done with treating the self message as a special type of message. So you could kind of encode your own message with a slightly different, embedding matrices compared to the neighborhoods. Or sometimes some network just consider them as the same kind of message and apply similar weight function over them. And you can try to think of different way of aggregating information between self message and neighborhood message. Where, like, again, you could simply treat all of them as the same and just operate the normal aggregation. But you can also treat them differently, such that you will basically have another layer of aggregation function between the two, like the aggregated neighborhood information and the self information. One such way of doing an aggregation is perhaps you could concatenate the two aggregate message and self message, and apply some transformation on top of that with, for example, MLP. And you can also simply do summation or average. So to put this all together, right? When we define a neural network for graph learning or graph neural networks, we need to define two operations. The first is how we compute the message. Second step is how we aggregate the message from neighbors and the information from itself. And we can also make the architecture more expressive by adding in a lot of these complex transformation functions, such as nonlinearity, like sigmoid and values. So then, if we revisit what we learned last time, right? This is the most simple and early version of a graph convolutional neural net, which does this simple linear convolution over the neighborhood space, right? You can see that here. The step here is kind of computing the message, where you weight you apply a fixed weight to the features or embeddings, and you divide it. You kind of do some normalization by dividing it by the total number of neighbors in the neighborhood, and this is the message that each of the neighbor is giving to the node of target. And the aggregation here is simply a summation. So in this case, actually the earlier classic or the earliest version of graph neural networks does not treat self information as a special type of information. So we just include the self information by like adding a self edge or like a self loop. So you always kind of treat your own information as part of the neighborhood and just apply similar weight to aggregate everything. Or sometimes it may even like drop the self information, which later became an issue. So kind of people come up with like the way of aggregating self information. And there's a extended or extension of GCN called GraphSage, which is not a single architecture, but kind of a line of a series of architecture that fall under a similar setting. Where for GraphSage, you can see that again, you start with computing the message and aggregating the message from the neighborhood, and you try to also like using some additional aggregation with the self message through this concatenation and the linear transformation, and at the end you apply this nonlinear transformation in the front. So you can see this GraphSage is designed to kind of aggregate the self information and neighborhood information with slightly more complex fashion than GCN. And you can also consider different message computation framework inside this aggregation function. For example, in the first version is basically, you can see the normal, very similar to normal GCN, where you just take kind of this average among the neighbors as the message computation, and then take the summation of them as the aggregation function. So this will basically fall back to the GCN that we talked about previously. But alternatively, there are two other ways of computing message and aggregating message. Perhaps one way is to, you can think about this using MLP to transform the message first, and then again taking the mean over the transformed message. And finally, you can also consider using some recurrent architectures as an aggregator. But here, because LSTM has kind of the notion of ordering from like left to right or right to left, even if you do bidirectional LSTM, it is still sensitive to ordering of the information. So what GraphSage does is it do a lot of data augmentation here. Basically, you need to reshuffle the neighbors multiple times. So when you learn this aggregation function, it does not memorize any ordering of the nodes, because you kind of shuffle the data throughout the training. So kind of these are very simple way that people came up with aggregating the message, and you could definitely, for each of these operator here, you can definitely add in more components as you need, and design different architectures. Particularly, the GraphSage also use a more normalization layers to solve kind of the gradient vanishing and gradient explosion problem. And in here, they particularly apply these L2 normalization to the embedding at each layer. It's kind of like a layer norm or like batch norm. It's more like a layer norm. So you regularize the embeddings of each node embedding such that it's centered and kind of normalized with the same scale and mean. And then another line of work is using attention, right? So considering the aggregation of message across a set of input. If we think about attention mechanism that we talk about in the transformer, right? It is actually like permutation invariant. If as I mentioned, if the weight, attention weight is only a function of the feature of the two node, and the weight does not have any information about the position or ordering of the node in the set. So this line of architecture called graph attention networks, or GAT, they come up with a better way of aggregating information that takes a little bit more information about the node itself, because in our previous architectures all uses kind of similar shared weight on the features. So this shared weight processing the message in a very similar fashion, which may lose some expressibility if you know you have a very different features, and some different features should be corresponding to slightly different weights. So that's kind of what the transformer architecture is able to solve, basically making your weight function a little bit more data dependent by adding these attention weights in front of the information message aggregation step. So yeah.
So why can't we just compress the thing into the message step, like into the weight matrix?
Mm-hmm. But you're not computing anything between the V and U, right? If you only compute message inside the U, then there's no way of measuring having a kernel between the current node and the neighborhood to adaptively up select or down select information, because you're still only using information of U, of your neighbor at this step, and you're learning with a fixed weight matrix W.
Oh, it's fixed.
Yeah, it's a shared weights, across all the nodes. Yeah, so the key change in the graph attention network is to apply a slightly more adaptive weight here, such that if each of your neighbor has slightly different weights. So I think the example below is a very good demonstration of the difference between GAT and GraphSage. So in GraphSage, you can assume basically the attention weight is the same as 1 over the size of the neighborhood or the degree of the current node, right? So it does not differentiate between different neighbors in the neighborhood. So it's basically explicitly designed or manually designed weight function that only reflect the property of how many node degree is associated to the current node. So if the node has a lot of neighbors, then you basically downweight everybody's information when you aggregate. However, we know that some of the neighbors may be more important than the other neighbors, right? It's similar to natural language. Even though you attend to all of the token in the sequence, but you're not necessarily using all of the information in these tokens, and the network will learn to rely on things that are more important. So you can have some level of sparsity or heterogeneity in this weight function. So the high level idea is if we apply attention, which is basically a function of some notion of distance or correlation between your current node and the neighborhood node, it might be able to extract the relevance of different neighborhood using the attention mechanism. And the goal is basically try to define a more arbitrary importance instead of using the node degree as the hand-picked weighting function. So the idea is first we compute the embedding of each node in the graph, and then we compute a weight for each pair of the node in the neighborhood and the current node. And this will implicitly specify some weights to different node in this neighborhood. And the attention can be can be written as different types of attention that we talked about previously, right? We talked about simply doing dot product, right? You could also concatenate them and learn some attention on top of them. And you could also apply some transformation and then apply dot product, just like how the transformer is doing it. So the weight matrix here is a bit like what's in the transformer. Basically, you also apply some transformation, like the weight here is, you can think about this as the key query value network that's kind of learning this embedding of the raw information or raw embedding. And you then apply this softmax attention. Basically, for each of the pair, you compute attention score, either through a dot product of the two, or you could apply MLP on the concatenation of the two weighted embeddings. And you average it, you normalize it with this softmax function over all neighbors. Such neighbors with higher attention score will effectively have higher weights, and we also guarantee that all the weights sum to 1, so it's kind of a weighted average. So the so this weighted sum is basically doing what's written here. So I think it's basically very similar to attention, except that here in the H of B, we don't necessarily include a positional encoding. Or if we want to be totally like invariance to permutations, we should not include any position encoding in the H of B's, such that all of this attention is only computed based on the feature itself and not the position of the node itself. Is this part of clear? I know that sometimes it can be a little bit confused, but this is slightly different than the attention in the transformer, where you don't define this neighborhood structure of where you apply the soft attention to. You just basically you can consider transformer as a fully connected graph, right? It's basically attention, the GAT applied to a fully connected graph. Questions?
Is there any work which does use like a positional encoding based on like the type of neighborhoods of the connected nodes?
Yeah, I think definitely there's there actually a lot of work that try to assign some positional encoding to the graph, because we don't want the graph sometimes to be just differentiating between some based on the local topology. For example, sometimes you also look at the global graph, which are hard to aggregate just with some local information. So you could apply some anchor node in the graph and compute distances to these anchor node and use that to do positional encoding. I think there's a paper called PGNN and I think IDGNN, which use like more advanced way of positional encoding. It's from also the Professor Yo, which is also a faculty in our department. They basically come up with different way of adding positional encoding such that you could add particular inductive bias in the graph network to differentiate some nodes that are non-differentiable with just this like fully invariant GNN. Yeah, that's a great question. All right, so again, the attention here does not necessarily be one type of attention. So I think a commonly used trick of computing attention in GNN is to do this like concatenation of the like key query values. Although this is kind of the same thing because you apply similar transformations, and do a MLP over the concatenated embeddings. This is slightly different than transformer, where a lot of time you use dot product as a way to cross-attend information. During training, we're going to train these linear layer, which is the transformation weight matrices for the attention. And this can be trained end-to-end and together with the normal graph learning objectives. And you can also use multi-head attention similarly, just define like different sets of parameters that used to compute 3 different attention softmax, and this can sometimes also helps. So this is the high-level idea of a graph neural networks, and particularly GAT, Graph Sage, and GCN. But in practice, you could, as I mentioned, you could think of very different ways of designing a graph neural network layer. It doesn't have to be any of the 3 that I mentioned just now. So if we consider this general layer design, you could break it down into this message transformation steps and the aggregation steps, where the message transformation step is kind of the key where you can come up with a very different architectures and inductive bias, and you can make it more expressive or less expressive by using different component of tricks that we use in normal deep learning. Some of the tricks include, for example, batch normalizations or layer normalizations, which we know will stabilize the gradient passing, the gradient backpropagation. And you could apply the dropout to the linear transformation of message to like alleviate overfitting problem. And as mentioned earlier, you could apply attentions or adding some nonlinearities like value or some other nonlinearities. And you could think of even like newer techniques of like computing some of like relative information in the graph. So batch normalization, it's we kind of talk about it previously, but basically you can think of like for each layer for each layers in the network, and because you have a batch of training data, usually you also have a batch of embeddings. The batch normalization here is just try to like apply additional like regularization to the batch of embeddings, such that within the batch they're somehow like regularized, and you can add additional scaling factors, like scaling parameters back to as an additional like transformation of the embeddings to give back the degree of freedom that you lost during this batch normalization. And dropout is usually kind of, you can think of dropout as randomly dropping pairs of edges from the message aggregation stage. Like basically, if you drop the message, of that neighbor, you kind of not taking that neighbor into consideration during this aggregation stage, and this is only a training time trick. So in inference, you still usually consider the full graph, unless you deliberately want to add some stochasticity into the graph. Although there's one special case where you do sometimes need some stochasticity, is when you have too big of a graph, where you cannot just fit every neighbors into your graph. In that case, you have to apply some downsampling strategies of your neighbors. Usually, we kind of deliberately pick like k nearest neighbors or k neighbors into consideration when we actually effectively compute this message passing, and how you construct that k neighbors can depend on some strategy you apply. For example, you could randomly downsample, and you could also maybe have some notion of weighting each of these neighbors, and you want to kind of weight them and pick the most relevant ones during the message passing. But a lot of this is related to scaling the graph neural networks in the case where the graph is too big. So now that we have kind of single graph neural networks, we want to think about making it deeper. So we recall previously when we talk about convolutional neural networks, it is actually not non-trivial to stack a lot of layers, and you have to make a lot of tricks, including the regularizations and like the normalizations and the skip connection. It's actually similar in the graph neural networks, but it has additional challenge to stack GNN layers. So if we consider the problem of doing message passing within one layer, we talked about previously that kind of one step of message passing is like aggregating information within a one hop neighborhood. If you do k layers of message passing, or we stack k GNN layers, that will effectively be propagating information across k hop neighbors. So of course, like there's no very special thing for how you stack the layers. So you usually just take the output of previous layer and feed them as node embedding to the next layer. If you don't do like very complex stuff, that we'll talk about in a minute. But if you think about this problem of doing k-hop information propagation, there could be an issue that we call over-smoothing or over-squashing problem that is more significant in graph learning. Basically, what over-smoothing means in the graph learning case is that we want these node embeddings to somehow like reflect some like local information or topological patterns of the graphs, right? But thinking about a case where you kind of over-propagate the information to like for too long, then like if you think about kind of the Markov chain Monte Carlo case, right? If you basically do your state transitions based on some transition matrix, and if you do that for a long time, you kind of will fall under some like stationary distribution where you kind of not moving further. It's a little bit similar here, where like if you propagating the information too much, you're basically repeating information back and forth, and so at the end you will observe that all of the node embedding become very similar to each other, and you're not able to kind of distinguish like very delicate local patterns among the graphs. So we call this like over-smoothing problems. And of course there are like more theoretical analysis. A line of order theoretically analysis is kind of a phenomenon, but here we just try to give it a very perceptual like understanding of why the problem happens, right? So similar to computer vision, we can define a receptive field in the graph neural networks, where the receptive field can be defined for each single node. If you look at the neural networks that embed each single node, we can basically consider like to compute the node embedding at this level, what are the input features of the nodes that are included into the computation of the current node embedding. And we can consider all of the sets of nodes that is used to compute the current node embedding as like the receptive field. So if we have a k-layer graph neural networks, it essentially have a receptive field of k-hop neighborhood. This k-hop does not mean like you go k step away from your node, right? You can basically make random jumps or random walk at each step. So you're not necessarily going further. You can like go back in the middle, but it's basically the neighborhood that you cover by making all possible k hops in your neighborhood. So that can cover a lot of point, and it can also cover same point multiple times. So the more we stack these layers, then the more we're propagating this information. And note that not just the single node carries the information from your neighbor, the other node that you're looking into also propagate information from its neighborhood. So for example, if you have a 2-hop neighbor, right, and if the 2-hop neighbor only carries information about itself, after you do the 2-hop aggregation of message, you will be only able to see the information like as much as like 2 hops away. However, that neighbor is also doing its 2-hop message passing, right? So by the end of like more message passing steps, this node kind of aggregates a lot of more information, such that when you again like take information from your neighbor, that might already contain information from like things that are further away. So so effectively you kind of smooth out your graph by having this message propagating within the node repetitively, and that is kind of causing the receptive field overlapping problem, where like essentially like for 2 node out of a graph, their receptive field becomes very similar after many steps of message passing, and this can be causing that if you have 2 nodes which have very similar embeddings, it's very difficult to kind of differentiate the nodes anymore. And that this is what perceptually lead to the over smoothing problem. But I think there's definitely like more theoretical work if you're interested in theoretical analysis of graph learning. You like basically search for literatures that describe this problem, define it in a more like rigorous fashion. So, but in this high level in this high level kind of perceptual of over smoothing, what the takes away of this is basically, instead of doing a lot of layers of graph neural networks, we can try to reduce the step of this message passing steps, and instead we want to make the architecture as more expressive as possible, but try to reduce doing necessarily a lot of GNN layers. So how are we doing this? A very simple way is to also, first, this is before we try to make the neural network stronger, but like in general, how we design the GNN layers is, first we can think about the tasks that we care about, like how big of a neighborhood we actually care about. And if we kind of know that this is a neighborhood or receptive field that I'm targeting, I will design a GNN with no too much, like with only a little bit bigger than what I need, without going into just blindly go to very deep graph neural networks, because that will eventually hurt ourselves. And the other thing is, maybe it's also possible to make your shallow GNN more expressive, similar to like LSTM and RNN, right? In RNN, we also talk about people usually don't stack RNN too much, but within each GNN layer, you could actually make your model a lot more expressive by playing with the different knobs that you can turn in how you embed the message and how you aggregate the message. So basically, the trade-off here is like try to increase the expressive power within each GNN layers. For example, adding more nonlinearity or transformations. You could perhaps make your embedding part, like message computation part, more sophisticated with more layers. Or you can also think about adding some layers that are not necessarily propagating information. So there is this position-wise multi-layer perception layers. This is different from the global MLP layers that we learned in the first lecture, where you apply kind of a huge, gigantic MLP at the end, that tries to look at information, aggregate information across different nodes. Here we're talking about a node-wise or position-wise multi-layer perception layer that only apply to the single node and transform information there. So you can consider adding this kind of pre-processing and post-processing layers that does not propagate information across nodes, which will alleviate the over-squash or over-smoothing problems. And the other thing is, of course, try to like borrow the information, try mimicking what the residual does for like convolutional neural networks, right? We can also add skip connections into GNNs. Basically, effectively, instead of going through this message passing layers, you could directly take the embedding and just skip that, the message passing with this residual connections. It's kind of like adding some shortcuts in your GNN. Question? Yeah, all of these operations, they preserve the equivariance. Yeah, if you think about, for example, like this is called position-wise MLP layers, right? So it's only operating at each single node, right? So no matter how you permute the ordering of the node, it doesn't matter. Like the embedding will move as with like how you permute the input.
How about like dropout?
So dropout is similar, right? It's kind of random, so it doesn't matter like how you permute your sets. The probability of this node getting dropped is always the same, because it's kind of defined without the notion of like knowing that this node is the first position and this node is the second position. Question?
So I guess I think sort of mentioned like adding like a information node or something like that.
Mm-hmm.
Does that cause the smoothing to happen faster? Or?
The information node, yes. If the information node has a lot of degrees in the graph, like that would be a bad thing. Like you basically want to avoid a node having super big degree. I think usually even if you have a classification node, it's usually only applied to the last layer of your GNN and not applied in every layer in between to avoid like over smoothing problem, I believe. But I think the anchor node or the position encoding is something different, because if you're not doing message passing, you're relatively computing some positional encodings. But I think that will sometimes break some equivariance a little bit. But I think most of the time the equivariance are guaranteed with these tricks. And that's also the challenge of graph neural networks and graph learning problem. Like when you design something, definitely first thing you need to check is whether you break this permutation equivariance and invariance. All right, so for the skips connection, again, this is also permutation invariance, or sorry, permutation equivariance, if you can see, because like once this is learned, like whether or not the edge is skipped, this layer is skipped or not, that's not depending on like how you order your input, because this operation will change with the similar way how you change your input. But like this skips connection is essentially very similar to what residual blocks does for convolutional neural networks, because effectively we're kind of doing a mixture of shallow GNN and deep GNNs, and we want to kind of let the model, give the model opportunity to like fall back to shallower solutions when it finds the complicated solutions not giving a lot of signal from this. So basically, if you think about what this self-attention does, this skip connection does, is it directly pass kind of the node embedding from your previous layer and add it to the message passing outcome in the current layer. So you can consider like if this is the h of L minus 1, then this addition becomes like HL minus 1 plus aggregation of the message. So it's essentially what we talked about in the prototype last time, right? So the vanilla GCN, it does not effectively have this skip attention. Skip connection. So it just blindly do convolution over the neighborhood versus the GCN layer we showed in the last lecture has this kind of additional term, which is basically what you get from the last layer. And by adding this directly to the aggregation outcome, you kind of effectively pass this skip connection.
Can you intuitively think that this is trying to add in information that's sort of unsmooth in the next iteration?
Exactly, yeah. You want to keep your original information, original version of the information in the node. Okay, so so here we kind of talk about like single layer skip connections, right? But similar to like kind of dense net or advanced like ResNet, you could define like more skipping across more layers, however you like, and at the end, like you could also decide very different type of doing aggregation of the node embeddings. All right, so I think last time one of you asked a very interesting question about like is GCN generalizable to new information? So indeed, GCN is inductive. So when we talk about transductive and inductive, basically transductive means if you train on the data and you will be able to predict something that's within the data you train on, or kind of in distribution. And transductive means basically generalizing to something that is never seen in the input data. And in the graph case, the inductive can be defined also at different levels, from node level, edge level to graph level as well. But the key concept here is since we're only defining and learning these sets of shared parameters that is used to do this local convolution of informations, it does not limit the topology of the graph that you can apply the model to. And that effectively means that with any new graph, for example, completely new graph that's not seen in the training data, as long as you were able to define this graph structure with the same type of node features and connectivity, you'll be able to apply the network trained on different graphs and extend it to the new graph. So this is what we call kind of like graph neural networks are inductive. For example, like you can consider graph level inductive capability, right, where you train on like one set of molecule graphs or small molecules and predict like the property of a given small molecules. And during test set, if you give it a completely different sets of small molecules that have not appeared in the training data, it will be able to, at least you will be able to compute predictions on these new sets of data, and it will be able to generalize to like all kind of unseen graphs that are not trained. This is kind of a graph level inductivity. And you could also generalize to new node, where, for example, in training time, you only observe a subset of the node or the subgraph of the entire like gigantic graph. For example, in social networks, right? And during the inference time, there could be a new graph, a new node added to the graph that is already existed. You can still apply your trained network on this new node to make connections. And with the introduction of new node, there's also new edge introduced in the setting, and you will be again apply the same architecture on the new edge. But here, since we changed the graph, by adding a new node or removing a new node, the connectivity also is changed. So in order to make predictions on this new node, we will basically start over from the beginning and redo the message passing from the beginning. Essentially, this is what we talked about a little bit last time. Like, we're not incrementally making predictions on the new node. Now, so to be able to make predictions on this new node, it requires computing or updating embeddings for multiple of the node in the network, because this addition of node changed the topology and connectivity of the graph. So it now becomes kind of a new graph. All right, so to summary, and also extend beyond what we talk about a little bit, we can define this graph learning process as a message passing process, or kind of a general message passing framework, where for a given graph noted by a set of node and its features, or node features f of I, here we only consider kind of like scalar features with the dimension of CV, right? And assuming we also have some edge features, the edge feature previously is defined as connectivity of the two node. However, in the more general graph learning cases, you can also have like attributions on the edge as well. Like the attributes on the edge can be, for example, a notion of geometry, like the distance, right? It can also be time, if you're considering temporal graphs, like some edges only form before or after some time point. And it can also be a weight, or it can also be a type. Basically, if you consider like relationships in the graph, like you can have like author-author relationship, and you can have author-paper relationship. These two are different types of edge, and you might want to treat them as slightly different types of message. So in general, like the graph message passing framework, if defined over this general notion of normal graphs, it can be considered as first compute some message over the information from the node and the edge, basically all three parties involved here, and then try to apply some aggregation of the information by doing some types of summation or like a weighted average or some aggregation here, and combine that with the self-information, and that's the aggregation step. And so at the end, each of the embeddings in this graph, each of the node updated its embeddings within the node itself. So you can see that in this message passing step, like what you're doing, essentially you can consider that as computing something, like put information, like broadcast your own message to the edges, and let the node to collect that information from the edges. Right, so this is more related to how you implement the GCN or graph neural networks, where essentially you start with the embeddings from last layers, you apply transformations to get like these transformed f of j and aij. You put them on the edges. So you define kind of an edge tensor or embedding that carries this information. And then you take the information from the edges defined by the connectivity and neighborhood and aggregate them to get this aggregated function.
Is there like an optimal number of edge attributes that's somehow related to the size of the graph? How do people go about defining the distinct kinds of edges? Like, what's stopping you from having like a high-dimensional vector that just basically captures like, an entire text description between two nodes?
Yeah, I think that's a good question. I think the design of the features is relatively, I would say, manual at the moment. But you can consider if you have too many edge types, right? Then for each type of edge, you will have an extremely sparse graph that does not carry a lot of information. And if you assign each individual edge a different type, then you only have a single edge in each of the graph. If you look at each type, so that's not aggregate information effectively.
What if instead of like just passing information like by edge type, you also passed it by like edge similarity? Like if you had like a high-dimensional vector that was like, say, a text description of like this gene does this, and then you have another somewhere else this gene does that, and they're both like in the same pathway or encoding to the same phenotype. Maybe if you did a dot product between those vectors of those edges, like they're similar, so you choose to pass that information.
So you have to know the information here is from the node to a node. So it does not necessarily compute dot product within the edges. So the information here has to be along the edge, but it's flowing from a node to a node. But with this aggregation step, you could use like solve attentions, like we talk about, right? Which look at different edges and try to weight them. So it's the aggregation step that kind of does this already inherently. But I think at the end, it's not usually the edge types that effectively determines the similarity, but rather the node features or node embeddings. So you have to distinguish whether you really generalize with similarity of the edge, or you're actually generalizing relying on the embedding from the neighbor. And when you do this edge, when you do this edge level weighting, you also need to make sure that the equivariance is not breaked, for example. All right, so now let's talk about something more specific. So consider this general graph definition, right? So what we've talked about so far is we are designing a very general notion of graph, where the graph can be defined by a set of noted as S, and some connection, which is the edges. And we're defining a very broad notion of features related to the node, where basically you can consider like each of the node takes in a d-dimensional features. And these features can be, basically these features are all numerical features of the property about the node, but they're treated as if each of them are like a scalar. So it does not have any notion in algebra, or like when you consider the space that these tensors are related, they're mostly like a single scalar values at each dimension. So you can do like very arbitrary operation to the scalar functions to compute another scalar features, which is the embeddings. But there is a particular type of graph where the node features are more special than just a normal graph. And that's what we call geometric graphs. And geometric graphs is very special type of graphs where the features in the node now have some special properties, which when we consider these properties, they have certain rules or equivariance or symmetries that is usually preserved when you observe these features in real world. And that additional constraint is added to this type of graph when we model these graphs. And one type of constraint is called geometric constraint. So now consider that each of the node now becomes an actual node in 3D space, right? So each of the node actually has a physical meaning in the 3D space. It has what we call geometric information, or you can use basically a vector that try to characterize the position of the node in the 3D spaces. And here you can also see like each single node here actually have a real notion of distance in 3D space, in physical space. In this case, you actually know that there are certain geometric attributes that we know that are computed in such way, and they're gonna be transformed. Also follow some rules if we apply transformation to each single of the node in this graph. So we call this type of graph geometric graphs, where we can consider this is a graph defined with a set of nodes embedded in the Euclidean space, which is kind of the 3D space that we're talking about. And each of these nodes is decorated with geometric attributes, which is the position of the node and some geometric features that has actual physical meaning in 3D space. And one such example is a vector. For example, velocity, right? So considering like each of the atoms in the small molecules, right? There will be different types of force that kind of, some of you are from physics, learning physics, you can probably know better what kind of forces there exist, but for each of these nodes, you can consider this kind of like a force field behind, and each of this node is moving in the 3D spaces, right? And they're moving in some direction with some velocities, and there's also forces that apply to the node such that the velocity will change in certain directions. And all of these velocities and positions of the node, how they move and change will follow the actual physical constraint. So that's why we're using kind of additional problem.
Is the adjacency matrix dense, meaning like it has all pairwise connections, or are we excluding some particular connections?
Yeah, that's a great question. I think if we consider graphs, it's a general notion of pairwise information, so it can be sparse and dense. So if you're using a transformer, for example, then it will always be a dense connectivity graph.
So it's sort of like kind of custom lattice.
Exactly, custom lattice. Yes, exactly. Yeah, I will talk about that in a minute. But before we jump to the, just assume that you already have some sparse or like defined, lattice amount of nodes. And what's different from the normal graph is that now instead of just using a scalar to represent each node features, we design these node features more carefully. And particularly, there are two sets of new features or feature types that we need to consider. One is the coordinates. The coordinates directly decide the position of the node in the 3D space. It's also a vector. It's usually depending on which D you're computing. Like you can move, if you move on a single line, then there's a 1D coordinate. If you're moving like in the image, you can also like rotate things in 2D space, right? That's 2D. But for a lot of more geometric graphs, that's very important in real world. We consider 3D space, so we just assume kind of D is always 3 for X. Similarly, you can define a set of vectors or multiple vectors, which we'll describe in the next lecture. We call it tensor, which is a more general notion of these representations, which are associated with the coordinate, and they're also defined in these 3D spaces. Basically, a set of vectors that characterize the properties that are relevant to changes or motions in 3D space. Some such geometric feature, one example is the velocity, and the other is like acceleration, like forces. So if we look at the graphs in real world, right, some of them are graphs, more general graphs, and some of them are geometric graphs. Like, for example, for the given graphs here, like, I want to ask a simple question here, like, which of them do you think is geometric graphs? You can name one, like, the molecule graph, exactly. Any more? point cloud, definitely, because it's the shape, everything that models the shapes is geometric graph. Any more? The physical system, exactly, like the many-body problem, right, where you want to capture a lot of these geometric properties. So, and exactly that, like, the three graphs on the bottoms are we call geometric graphs, and the graph on the top where you only care about like normal like relationship and more general relationship, which are not confined by 3D physics, or we call general graphs. And such graphs can be, for example, the pathways or gene interaction network that some of you are like try to do research on. Like they're kind of a more general case of graphs. But the geometric graph is really a very special type of graphs. So, I mean, by saying that geometric graphs is more special than general graphs, you can see that the architecture that is used to learn the geometric graph is actually less expressive than the general graph. But it does not make the problem easier, because when you deal with a less expressive family of models, that means you want to add more inductive bias in the model. And how we design this inductive bias such that its compliance to these real physical constraints is a hard problem. It doesn't mean this line of work is more expressive than graph neural networks, right? So if we consider neural networks, graph neural networks, we talk about a basic property that we want to guarantee is the permutation invariance and equivariance, right? So if we consider geometric graphs, it also needs to, because it's a graph, it also has a similar property, which is permutation invariance and equivariance. So when we represent geometric graphs, we should also already like handle the permutation, equivariance, and invariance. However, in addition to these sets of permutation, invariance, and equivariance, there might be additional invariance and equivariance that we now need to comply to compared to the general graph, which these kind of new transformations are not important. So this is motivated by actually a lot of the real-world constraint in physical space or in physics. For example, I think usually we call it symmetries in physics, right? So two of the very important symmetries that the geometric deep learning community try to learn to fulfill is translations and rotations. So consider like things in the 3D coordinate, right? If you consider your graph as a set of point in the 3D spaces, translation means like a fixed movement or a movement in the straight line is applied to each single 3D coordinate of that system of nodes. So I think that the translation is the hardest to draw, like, but consider you have something here, right? And you move all of them together as like, consider them as a rigid body, so everything is chained together, right? And you want to kind of push the whole thing together towards the right-hand side. Then you're moving along this line, right? So this operation is called translation, right, in the space. So so if you think about a molecule in space, like it doesn't matter if like it's here or it's there, as long as it's in the same conformation, right? So this is what we call translation invariance, where like the physical, this translation of the 3D coordinates should not change the vectors and geometric vectors on these molecules. So this is basically the translation transformation on the coordinate system does not change the property of the graph. So this is what we call translation invariance. And similarly, if you consider the the force vectors or velocities, right? You could apply similar force or similar velocities regardless of where the molecule system is located. So it's kind of also invariant to this translation. However, the coordinate does move with the translation. So we can consider as kind of doing some linear operation to your 3D coordinate as considering everything together as a rigid system. The other thing is called rotation, or reflection is also one set of symmetry groups that we consider in physics. So rotation, it's more kind of easy to visualize here. Basically, like again, treating them the whole system together as like a chained, hard, rigid body. Rotation means you're applying some rotation transformations on this rigid body system, such that their coordinates will rotate with respect to some origins. And usually we can, in this Euclidean space, we can define a rotation matrix where if you do kind of linear algebra, right, with applying this rotation matrix to your coordinates, then effectively you kind of conduct this rotation transformations. And when we consider this physical system of rigid groups of points, no matter how you rotate them, their properties should remain the same. Like it's kind of the same graph if you view it in this way or like in this way. But something does change. Like all of the geometric vectors are rotated in the same fashion as how you rotate the whole coordinate system. So for example, the velocity, right? Now if you have a system here and there's a velocity pointing towards here, when you rotate the whole system, the velocity will rotate in the same way. We're basically applying the same rotation transformations, and that's what we call equivariance. So again, like these words seem very similar in the graph learning, but now in addition to permutation, we also define additional groups of transformations, including translation and rotations, where we also need to handle this equivariance carefully when we use deep learning, taking these vectors as the features as input. So there's this a concrete example of a small molecule, 3D atomic system, which involves like a small molecule. If you see, like in the normal, like the first step is related to kind of permutations, right? That's what the normal graph preserves the equivariance and invariance with respect to, right? If you just like note each atom with a different order, that shouldn't change the atom at all. Like it's just the way kind of you represent the features of this atom with a different order, and that's what we've learned so far is with permutation invariance. So the potential energy or all of like the physical properties that we compute on the same graph will be exactly the same. So this invariant to this permutation operations. And if you look at the features that are scalar, for example, type, right? The positions also permute accordingly in this representation, so we call this permutation equivariance with respect to the permutations. And if you look at the geometric part, the 3D coordinates will be permuted similarly. So we also preserve the permutation equivariance in the 3D coordinate space. However, if we apply rotation, right, this is more different now. If we apply rotation to this whole system, then the potential or the energy is remain exactly the same, right? So because like it's the same molecule, you're just like looking at the molecule from a different angle, right? Or basically choose a different coordinate system to look at the small molecule. So the energy does not change. So you can see that the energy function is invariant to this 3D rotation transformation. Similarly, the atom types does not change at all. Like however you move this, the atom type is exactly the same. So you can see that potential energy and atom types, which are a scalar feature of the node, they do not change with this rotation operation, so we call them rotation equivariant. However, if you look at the 3D coordinates, right, if you rotate the system, the coordinate will change, and the coordinate is rotated in the similar way as how you apply rotation to the whole system. So we call that the 3D coordinate. These features are permutation equivariant with the transformation of rotation. Any questions here?
Do we ever consider transformations that don't change the coordinates but change some other feature? Like
Yes. Oh, velocity.
or probably not velocity, but for example, like would the Potts model fit under this framework? Because in physics it's changing spins, but the lattice points are fixed.
So I think that's more related to the scalar vector, and it's because it's not, the function of geometry, which is a function basically of the distances and 3D locations of the point. So those are not geometric features or attributes, and therefore we do not apply. So the things we talk about here, rotation, transformation, these are all transformation applied to the geometric vectors and geometric tensors. So it has to be it has to be operable in the geometric space. So I'm not sure, like, I don't think spin is such case. I think spin is something different. But you could definitely define,
Maybe that's
like,
a bad
yeah.
example. Just thinking something that might change, like that particular node in the graph, but
Yeah.
we just rotate like that bounded vector nodes.
A good example of that would probably be like nanchomers, for example.
Sorry, what Mars?
Nanchomers, like different, you have like different chiral properties, but you have like the same molecule graph, but they're non-superimposable. Like one will reflect like polar light along one axis, and the other will reflect it along another axis. Because for proteins, for example, I think like the functional group is like oriented in the opposite direction or something. Like
So the translation and rotation I'm talking about here is applied to the whole groups of atomic system, treating them as a rigid body move. So what you're talking about is you make local rotations to a subset of the rotamers.
Yeah.
Yeah. So that is slightly different than what the translation rotation equivalence we're talking about here. So if you consider that group, right? If you only look at the local structures without looking at how it changed with respect to the global sets of point, in the local structure, it still have some rotation and translation equivalence. But if you only move part of the system with that permission, then you don't have that equivalence anymore, because we're talking about moving the whole body as a rigid sets of point. All of these groups, all of these group operations are defined on the rigid body of the rigid body group of elements. Any further questions? Yeah, this can be the most difficult part. Yeah.
Are there methods that account for a molecule's ability to like change conformation slightly? For example, if it's flexible or able to rotate around a certain bond?
Yeah, I think that's essentially what the same question here. So because the operation is not applied to the entire molecule as a rigid body, it would be considered a different graph. Yeah. Unless you could consider, like, for example, some of the steric thing is like you have something here and something here. So if you can apply, for example, a complete symmetry, like if you just flip it with like a mirror, basically the reflection operations, or you can consider this conformer being kind of a rotation of this conformer, then they're the same thing. They're kind of, sorry, the reflection is not. Rotation is, if you can create one conformer by rotating the whole thing together along the axle, then they're the same thing. It should be equivalent. It should be equivalent with respect to coordinate, and should be invariant in terms of, like, these two are the same conformer basically. You just rotate them, but the reflection is not. Yeah.
Yeah, some like reflections don't. That means like we're not dealing with rigid bodies.
We're still dealing with rigid body, but with a different operation. Like it's a reflection operation. So it's not rotatable. It's not. The matrix is different for reflection, and we're not dealing with reflection equivalence in the geometric deep learning architecture that I'm talking about. We mostly still deal with rotations and translations.